Hey, my name is Parker Duckworth. I'm a director of engineering here at Weaviate, where we're building the Weaviate vector database. And today I'm excited to share with you some of the scaling challenges that we've come across while building Weaviate and some of the solutions that we've come across in order to solve these, and then maybe look ahead as well at some of the future challenges of vector databases. So let's get started. Why are we talking about vector databases at all? It's a great question. And I think this can be easily attributed to the fact that the popularity of intelligent retrieval has exploded. I mean, we're in the era of ChatGPT, and we've seen the sophistication of models grow exponentially over a short period of time. Also, looking at the modalities of media being vectorized, I mean, whether it's text, images, audio, video, infrared data, geolocation, you name it, it's being vectorized. And as a result, vector DBs are sitting at the core of many search engine, RAG pipeline agentic workflow use cases. And we've truly seen vector retrieval go from basically the plaything of data scientists to a core component of critical frontline infrastructure. So today we're gonna, as I mentioned, look at some of the scaling challenges we've come across while building Weaviate, some of the solutions that we've come across in order to solve them. We'll take a quick look at some of the lessons that we've learned along the way, and then look at some of the exciting new challenges that we're looking forward to tackling in the future. So, challenges and solutions. What actually makes vector databases hard to scale in general? I think this can easily be categorized into two different categories. One, the shared challenges of all database systems in general, looking at maintaining consistency in a distributed system, workloads evolving over time, and two, challenges that are unique to vector databases specifically. So, for example, the requirement of storing high-dimensional data, the requirement of filtering on fuzzy semantic search and keyword search together, and the rapidly changing landscape of large language models in general. So first, taking a look at consistency in distributed systems. So within Weaviate specifically, all cluster nodes have to have a consistent view of the schema at all times. So if at any point two different nodes have a different view of the schema, this can result into some serious issues like data loss or data corruption. And we need to make sure that the schema is consistent across the entire system. It's also a challenge to keep up with rapidly changing data that's being replicated. If you have node outages, if you have network partitions, you can imagine it's very difficult to make sure that all data is replicated properly to all replicas. And lastly, the consistency level is a major factor too, because it's a big trade-off between performance and the level of consistency required for the client application. So how did we solve the consistency requirements at the schema level? We decided to use the Raft consensus protocol as the backbone of the schema propagation within a Weaviate cluster. Raft is nice because it provides strong consistency guarantees for schema changes, but it also very gracefully handles node restarts and automatically handles nodes rejoining the cluster. Object replication has a little bit different of a different set of considerations though, because objects change much more rapidly than the schema typically. So one aspect that we looked at improving object replication or consistency in general is through tunable consistency. So we opted into to engineer Weaviate such that consistency level is tunable at the query level. This means that you don't have to set a consistency level at runtime. You don't have to make any config changes. Basically, depending on the needs of the query at any given time, if you need to optimize for fast writes or for consistent writes, or if you want a more balanced approach with a quorum of nodes, then you can set this per query. Now you can imagine with replication, there's, as I mentioned, always going to be issues in a distributed system. Nodes are not always available all the time. And so there may need to be some repair mechanisms to ensure that objects are consistent across an entire cluster. So we introduced a couple of different replication repair mechanisms to solve this. Our first step towards this was a repair on read mechanism that basically when a node determines that it's missing an object based on the responses from other nodes in a cluster, it's able to repair that object on itself. However, the downside to this is that data is really only repaired when the node knows that it's missing the object, and that's not always the case. So we took this a step further with async replication, which is a background process running at all times, ensuring that data is consistent across all nodes. Now, as a background process, it needs to be something that's very lightweight, something that does not bog down the critical database operations. And so we based the async replication implementation off a Merkle tree or a hash tree, which is a very, very fast way of exchanging root hashes across all nodes to make sure that each node has a consistent view of the data at all times. And if not, then the hash tree is traversed down to the leaf node, and that represents a subset of objects which are exchanged between nodes and repairing all object inconsistencies basically in the background in a very efficient way. The next challenge I'd like to talk about is evolving workloads. So with most database systems, new users are going to start with small collections. This is especially true with vector databases, considering that vector databases are such a new technology. People are going to want to prototype, users are going to want to run POCs to make sure that the vector database is meeting the needs of their application. So we need a very lightweight, cost-effective way for users to onboard onto the platform that still provides good performance, that also scales to meet the performance needs as the collection grows in size. This is particularly difficult with vector databases because there's not a single vector index type that is both cost-effective and performant at all scales. So for example, you could have an index type that's very performant at large scale, but very expensive, or one that is very cost-effective and works great at small scale, but does not scale well from a performance perspective. And additionally, we need to support multi-tenant use cases as well. So to solve this issue of a not one-size-fits-all vector index, we introduced the idea of dynamic indexing. So the point of dynamic indexing is that we start with one kind of vector index that works well for small collections, and this index type is changed over time in the background to meet the needs of the collection as it scales up. So for example, we start with what we call a flat index, which is basically an on-disk vector format, works very well for small data sets, and is very cost-effective. It's a very cheap type of index to store. But then once you cross a configured threshold, let's say 100,000 vectors, the index type is automatically promoted to a very, very performant and equally expensive in-memory HNSW vector index in order to serve very high performant queries at large scale. And so the point of this is we don't want to charge a lot for an overkill type of vector index to a new user who's only trying to use the database at small scale. And we also want to allow a seamless scale-up experience as the collection grows. The performance doesn't degrade over time. So this allowed us to provide a really cost-effective, high-performance querying experience at all scale levels. To dive a little bit deeper into this, I think it would be useful to look at a real-world situation, a real-life scenario of how this might look. So say you have a new user for a vector database. They insert a couple thousand objects. These objects are still being stored in the flat index. It's all on disk. It's all very performant at small scale, and everything's fine. It's not costing them very much. It's a good experience overall. As the collection grows in size, vectors are inserted. We cross a promotion threshold. Let's call it 100,000. HNSW begins to build in the background. And once this process is complete, all future inserts and queries are routed directly through this HNSW index. So as the collection scales to millions or hundreds of millions or billions of vectors, performance doesn't suffer, and the entire application is able to scale and be very performant. So speaking of multi-tenancy, luckily with the way that Weaviate was designed, it was designed very modular from the beginning. And so we kind of got logical and physical isolation for free. So taking a step back and just looking for a quick second at how Weaviate's architected, you have one index for one collection. This is the basis data structure for a collection in Weaviate. It's called an index, and each index is made of multiple shards. Each of these shards are logically and physically isolated. Now, in a traditional single tenant use case, each shard is going to be responsible for just a subset of non-overlapping data. But from a multi-tenant perspective, we are able to map a tenant directly to an individual shard so that each shard is responsible for only one tenant. So therefore, there's no row-based isolation, let's say, from a relational database standpoint, but only table-level isolation. So there's no physical commingling of data whatsoever across tenants. Also, this modular design has really lent itself to allow us to scale multi-tenant at a very, very large scale. So for example, it only takes 20 nodes to very comfortably support 1 million tenants. Now, looking at multi-tenancy use cases, traditionally, out of all possible tenants, only a small number of tenants are active at any given time. So if you have all tenants warmed up in memory, in cache, hot on disk, ready to serve requests, you're wasting a lot of resources and you're spending a lot more than you would need to spend if you were able to optimize somehow only for tenants who are active at any given time. So we introduced some cost savings ability with the way we handle tenants based on the activity status of the given tenant. We do this through multi-tiered storage. So for example, if there's tenants that are inactive for a given period of time, they can be offloaded directly to object storage, removed from disk, pulled out of memory, and save a ton of money when this data is not being accessed whatsoever. When the tenant comes back online, a request can be sent to warm the tenant back up, and the tenant can be loaded back into memory, loaded back onto disk, ready to serve requests in a very short period of time. This really allowed us to reduce storage costs, not only for ourselves, but for our users, and still offer performance that is needed at the application level. So the next challenge, which is the first of the challenges unique, I would say, to vector databases, is the requirement of storing high dimensional data. Now, this really boils down to efficiently storing and retrieving massive data points. I mean, if you look at an individual vector, there's thousands of dimensions. One single vector can be many kilobytes of data. If you extrapolate this to millions or billions of vectors and their accompanying objects, you can imagine the storage amplifications of this type of data. So very quickly, we see that disk I/O becomes the bottleneck at ingestion. It's super expensive to hold even a trivial amount of objects in cache. So how do we address this situation? Well, we looked into leveraging vector quantization to do so. Vector quantization is basically just reducing the memory footprint of a given vector. Traditionally, vector embeddings are represented as arrays of 32-bit floats, and quantization, one, reduces the size of the vector embeddings by replacing each of those individual dimensions with a smaller size numerical representation, such as an 8-bit integer or even a binary representation. And two, some quantization methods also reduce dimensionality in general. And so Weaviate supports a couple of different quantization techniques. The first one that Weaviate supports is product quantization, or PQ. Basically, how product quantization works, it takes each vector and splits it into individual segments and then quantizes those segments individually. This is nice because it provides a high ratio of compression and also still maintains a very good recall at real-world scale. The next is scalar quantization, which maintains dimensionality for the vector, but replaces each 32-bit float dimension with a smaller numerical representation, such as an integer. And lastly, we have binary quantization, or BQ, which replaces every single dimension with a binary representation. The next challenge I want to look at is property filtering. But it's not just property filtering, it's property filtering with semantic search. Now, this is tricky because semantic search is fuzzy. It's not exact, and ANN is approximate by definition. But in spite of this, real-world use cases demand filtering by properties on exact matches and on ranges, for example. So we need to find a way to take this fuzzy search and still find exact deterministic ways of searching. And on top of that, the properties have to be stored and retrieved efficiently alongside these vectors. So the approach that we decided to take was in providing a hybrid search functionality. So hybrid search works by fusing together result sets from both semantic and keyword search, which are conducted in parallel, and fused together using a fusion algorithm that includes a scoring mechanism. This is great because where semantic search falls short with its fuzziness and where keyword search falls short with its inability to include context in the search, the combination of both is really the best of both worlds. After introducing hybrid search, which became a very popular way of searching, probably the most popular way of searching on a vector database, we determined that actually the keyword search was the bottleneck. Our vector search scaled very well, easily into billions of vectors, but we saw that the BM25 implementation, which is the algorithm behind our keyword search, was not able to keep up with the performance of the vector index. So we looked around and took inspiration from the best full text search engines out there and discovered this really great improvement on BM25 called BlockMax Wand. Now, BlockMax Wand is basically an algorithm that works with BM25, and it groups posting lists together into blocks and assigns a max score per block so that blocks can be very, very quickly skipped, and we can very, very quickly skip over irrelevant documents that don't contain the phrases that are actually used in the search. So with the combination of hybrid search and BlockMax1 based BM25, we were able to provide a hybrid search that scales super well into the billions. Speaking of property filtering, our property filtering relies on inverted indexes. And our inverted indexes are used to build the allow list of doc IDs that the vector and keyword search uses to immediately discard any documents which are not relevant to the search. Now, we also saw that our property indexes were not scaling as efficiently. We took an initial look at traditional bitmaps as a way to solve this, but unfortunately with bitmaps, you see that over time with evolving data, bitmaps become sparse, and there's very poor efficiency for sparse data with traditional bitmaps. So we dug a bit further, found some research papers on a concept called roaring bitmaps. And roaring bitmaps are a great improvement upon traditional bitmaps because not only do they handle sparse data in a very efficient way, but they also still provide the very fast bit set operations with near constant time performance that you would expect. And the next challenge, and the last one that I would like to discuss in this talk, is the rapidly changing landscape of large language models. As we've all seen, models have become outdated very, very quickly. It seems like there's a new model every single week. In fact, there probably is. It's difficult to keep up with this rapid change. Additionally, embedding service APIs are not known to be super predictable. It's not uncommon to run into breaking changes without notification, for example. It's messy to keep up with them. And on top of that, the types of vectors are rapidly evolving as well, not only in terms of dimensionality, but also in the way that vectors are represented. For example, there's a new concept called multi-vector representations, which is basically a vector of vectors that's becoming very popular with models such as Cole-Pauli and Colbert. The way that we deal with this in Weaviate is through model flexibility. The vector database has to be very, very flexible with its use of models. Now, one way that we can do this is through providing many embedding provider integrations. Here's a small subset of the embedding provider integrations that we support. There's a much larger list on our website. And in doing so, we constantly keep up to date with the new embedding providers and the new models that they provide. And it also abstracts away the messy embedding service APIs. All you have to think about is putting objects into Weaviate, and Weaviate will handle all the vectorization behind the scenes. Another way we're flexible with models is by enabling multiple vector indexes per collection, or in other words, multiple vectors per object. So say, for example, you have a collection vectorized with GPT-3, and you want to test how your system is going to behave with GPT-4o. You can simply add a new vector index to your collection and add the GPT-4o derived vectors to your objects, and away you go. And to add even more flexibility on top of that, we added the ability to select the generative model at query time for RAG queries. So if you want to try out different generative models for your RAG queries, you're able to try new models on basically a query by query basis at runtime. So let's talk about some of the lessons that we've learned along the way. Well, for one, it's very obvious that vector databases have to keep up with the innovation of the AI subset of the industry in general. AI is moving so fast, LLMs are moving so quickly. The vectors of tomorrow may look nothing like the vectors of today. So we have to make sure that the infrastructure evolves with it. Like most tech, scalability isn't just about throwing bigger hardware at the problem. You need to write better software. And this was especially true for us at Weaviate while we're building our vector database, because we very, very quickly hit the limits of vertical scalability of disks on cloud service providers. So putting a strong focus on horizontal scalability and writing very clever, very performant software has become key. Also, we've had to really place an emphasis on getting creative. LLMs, vector databases are relatively new in the industry, and there aren't a lot of existing solutions. So we really have to think outside of the box in the way that we approach problems. And lastly, we not only have to build for today's scale, which is massive, but also we have to keep things flexible enough to evolve with the landscape over time. So now what's next? I mean, let's talk about some of the future challenges that we'd like to solve with vector databases. As I mentioned earlier, multi-vector processing is becoming more and more prevalent. Like I said, this is basically a vector of vectors. So forget about a single vector with thousands of dimensions. Imagine a vector of hundreds of vectors or thousands of vectors with thousands of dimensions. You can imagine the storage implications of that. This is something that we're already taking into account because we don't see this going away. And it's something that vector databases must be able to support into the future. Next is the streaming ingestion. Not only looking at low latency indexing, but also looking at ways to separate storage and compute, or in other words, to independently scale read and write workloads. We've talked a lot about software, but also there's massive innovation going on with hardware. So keeping up with the newest GPUs, the newest disks, hot new ideas like RAM disaggregated systems. I mean, these are all things that vector databases need to be flexible enough to adapt to. And last, as I mentioned, in-memory vector indexes are very, very performant, but they're also very expensive, and they don't scale super well. So we're always keeping an eye on the latest improvements and innovations in disk-based ANN algorithms, because we think truly either pure disk-based or hybrid vector indexes between disk and memory are the future for scalable vector indexes. So that's it. You can find me or Weaviate on these various social media locations, and thank you so much for joining.